All right. Check recording. Yes, we are recording. So when we left off, I said we were going to talk about stationary phase types. As you can imagine, there are a number of them. Okay, each type of stationary phase behaves differently, and we will sometimes call the technique a little bit different by a different name as well. Okay. But unlike in, liquid-liquid extraction, our stationary phases don't move. Okay, so our chromatography, or if we look at different types of chromatography, right? We can also look at the action method for that type of chromatography, right? And then we can look at common instrumental methods for which it's employed, right? And then we'll talk about common stationary phases. So, adsorption chromatography will separate analytes based on the adsorbance of the analyte molecule onto the surface of the stationary phase. Okay, we see this a lot in GC. Okay, we can also see it in HPLC. Okay, HPLC stands for high performance liquid chromatography. You will also see RP HPLC, which stands for reverse phase HPLC. We'll get to what that means later. Okay. Common stationary phases for this are going to be things like divinylbenzene, right? C18 in the case of liquid chromatography, right? Other things like that silica, right? Silica, okay? Then we have partition chromatography, right? Partition chromatography. And this is where our solute equilibrates, right, between stationary phase and the mobile phase. Okay. And in this case, the stationary phase is a stationary liquid. All right. It's a stationary liquid. It's almost exclusively used in GC. Okay. And the most common stationary phase is going to be carbowax. Right. It's going to be carbowax. So the GC column that you used in organic chemistry is a carbowax column. And that is actually a little particle that's coated in a thin layer of wax. And when the column gets heated up, this becomes a liquid layer. Okay. And so your analyte was partitioning in and out of that liquid layer into the helium carrier. Okay. So that's partition chromatography. It's different than adsorption chromatography because in adsorption chromatography, we're talking about the analyte sticking to the surface of the particle and then coming out. Okay. So there's no penetration of the solute into, or the analyte into, the stationary phase particle. Okay. All right. Then we have ion exchange. All right. You all have ion exchange stationary phase in your refrigerator or in your, uh, you know, uh, water filters, right? These are going to be based off of ionic or electrostatics. Okay, all right. And we use stationary phases that are highly charged anion or cation. Okay, functional resins. All right. This is pretty much exclusively HPLC. All right. You use the same instrumentation that you use for HPLC, but your mobile phase will be slightly different. Okay. Um, and the stationary phases are resins, right, with charged functions, charged functional groups. Okay. We can also have molecular or size exclusion chromatography. Okay. And this uses a gel with controllable pores or controllable pore size. Okay. And things that are bigger than the pore size will take a very quick route through the stationary phase. And so, they get eluted very quickly. Whereas things that are smaller than the pores will take a very circuitous route through all the different little pores in the column, and so they come out very, very slow. Okay. There's no real instrumental methods that use this, although UV vis detection is often employed. This is typically done as a column inside of like a hood or on the bench top, um, and it's pretty much all done with Cephadx gels. Okay, um, it's a biochemical technique. Okay, it's a biochemical technique. All right. Um, Likewise, affinity chromatography is another biochem technique. All right. And so there's no real instrumentation for it, but the or the solute is separated based on its affinity with an antibody. Okay. So you have a stationary phase that has little antibodies sticking off of it, and your analyte will bind. And then you release it by denaturing uh, the antibodies. Okay, or putting on something that binds even tighter to the antibody. All right. We're going to focus on the liquid chromatography and um, gas chromatography side of things. Okay. But first, let's look at a chromatogram in more detail. Okay. So most chromatograms will have a few key things to look at. Right. So of course we have our retention times. Right. And then here we have our void volume. Okay. Um, which in your notes from lab would be TM, right? Okay. This is the time it takes for unretained molecules. Okay. And it is the difference in the time from injection. Okay. Right. So the injection time is typically we set to 0, okay? And it is the time from injection to the time it takes an unretained molecule to come out, all right? It is the minimum time a molecule can hang out in the system, period. Everything that goes into your system stays in at least for T sub m, okay? The retention time is the difference between the injection time and the peak time for an analyte. We also define an adjusted retention time, which is the retention time minus the void time. Okay? It's a valuable thing to know. Okay? If we look at relative retentions, okay, relative retention values are symbolized as alpha, okay? And we set that up always so that it is greater than 1, okay? So alpha is greater than 1 always. All right? Always. And this essentially a relative a relative retention just tells us, you know, how much more is compound 2 versus compound 1 retained on our stationary phase, or compound 3 versus compound 1, right? Okay. We also can define the retention factor, okay? So the retention factor is the relative retention time divided by the void time, okay? And if you need that broken down just a little further, it's the retention time minus the void time divided by the void time, okay? Now that will tell us, essentially the affinity that our solute has for the stationary on its own, okay? So another way of writing our alpha is K2 divided by K1, all right? We can also define a retention volume, okay? And we can define that as the retention factor times the mobile phase flow rate, okay? Or the void volume. Sorry, void volume. K times the void volume. Or the volume needed to elute, the elution volume. How do we get that? Well, the elution volume is the retention time times the mobile phase flow rate. Right? And we give that the symbol V sub r. Okay? So our flow rate in mil per minute times the number of minutes it takes for something to come out of the column gives us our retention. Okay? Now, we can look at a few things that happen, all right, in a column. Right? We can look at the resolution of two peaks on a column. Okay, we give that the symbol R, right? And R is going to be the difference in the retention times for our two peaks divided by the average of their widths. Okay. Alternatively, you can use retention volumes. Okay. Or if you don't have access to the peak width, you can adjust the equation to use the retention time and the width at 1/2 height. Okay, computer, are you gonna stick that back on there, or yeah, that's what don't mind the memory effect of my computer. Okay, so we can use the width at 1/2 height if we can't get or the average width if we don't have access to the actual peak widths for some reason. Okay, if R is greater than 1.5, okay, we say that the peaks are baseline resolved. Okay, and what this means is that in our chromatogram, there is sufficient distance between the two peaks that there is no significant amount of overlap. Okay, for R less than 1.5, okay, you get varying degrees of overlap. Okay, and so you know you would start seeing things maybe like this, and then like this, right, and then that, right, and so this would be increasing R values. Okay, and you can imagine that each of these peaks kind of falls into the other. Okay, here there is 0% of this happening, right? Here, it's still very likely that they're baseline resolved, but here, that looks like there could be a little bit of overlap in this region right here, right? Whereas this, there's clearly overlap. Okay, all right. If you look in your analytical book, okay, so in Harris, okay, figure 23, -10, okay, shows you an excellent image regarding this topic. All right. Okay. Another thing that happens is we get band broadening. Okay. So if we look at a single analyte, and I don't know why that didn't, right? But whatever. If we look at a single analyte that is being flowed over through a column, okay? When we initially start, right, we inject it as a very tight peak, right? Very concentrated. Over time, what happens is that peak starts to spread out. Okay? And as it goes down the column, that spreading gets worse. All right? And so our chromatogram takes on different shapes, right? So here we have a very tight peak. Here that peak is a little broader, a little bit lower. Here that peak is very broad, very low. Okay? And that is increasing time. Okay? Until finally our peak is eluded. All right? And we could go over the details of that. And we will. We will. Right? There is one of the major contributors to band broadening is diffusion. Right? We should all know what diffusion is by now, right? This is movement across a concentration gradient. It's movement across a concentration gradient. And it is governed by Fick's laws. Okay? It's governed by Fick's laws. First law states that the flux the flux, which we symbolize as J. Wow, that is a horrible J. What kind of J was that? That didn't happen. You saw nothing. Okay. We symbolize that as a J. Okay. And that is going to be equal to the diffusion coefficient divided by concentration gradient. Okay. The negative symbol here implies that movement occurs from greater concentration to lower concentration. Okay. And so really, you can think about it. Wow, my drawing skills are just not on point tonight. Or today, excuse me. You can think about it as movement through a unit of volume. Right? The flux is the movement over time, right? From position X to position X plus dx, right? At concentration C, over here is C plus dc. Right? So this has a width of dx, right? And the difference across here is dc. Right? In this equation, we treat our concentrations as moles per cubic meter, and we treat our diffusion coefficient then to be meters squared per second. All right. Now we can relate the diffusion constant, to temperature and relative friction. All right. The temperature, it gets related to by Boltzmann's constant, little k. And that gets multiplied by the temperature. And then we divide that by the coefficient of friction. All right. And the friction, the coefficient of friction in a fluid can be modeled as 6 pi, all right, times eta r. Okay, where eta, that's why I'm having so many problems. Eta is going to be the viscosity of the fluid, right? And r is the radius of a spherical particle. Right? Most of the time, I would not expect you to compute this stuff here. I would probably give at least this to you so that you could compute this and then compute the flux, but honestly, I'd probably just give you the flux. Okay? All right. But we can look at the chromatic brand's concentration profile, all right, being equal to the number of moles divided by the square root of 4 pi times time times the diffusion constant, all right, times e to the negative x squared divided by 4 dt, okay? And so the concentration, all right, in moles per cubic meter can now be made into a function of the distance traveled in the column. All right, got another couple minutes. All right. So that's one aspect of band broadening. Okay, that's one aspect of band broadening that we need to consider. There are others. There are others. All right. So the total equation that describes the action of band broadening is called the Van Deemter equation. All right. And that says that the height of a theoretical plate in the column is going to be equal to a function of the various path lengths in the column plus the longitudinal diffusion coefficient divided by the flow rate plus, okay, the two components of concentration change, okay? Which is what relates back to Fick's law. Or I should say the mass transfer. These are mass transfer. Right? So here we have diffusion. Here we have path lengths. Okay? All right. Now I know that that is not immediately obvious. Okay? So we're going to consider each of these terms in turn. We already discussed diffusion. Okay? And remember that U here is going to be the column flow rate, or the mobile phase flow. Right? So we can minimize diffusion by really ranking up that flow rate, but then we enhance mass transfer problems. Right? So we'll deal with each of these in turn. Okay? I'm just going to keep the Van Deemter equation up here. Right? So, A, right? This is the path length variable. Right? And you might be saying, well, what does that mean? Right? So what you have to keep in mind is the stationary phase in a chromatography column is really packed up particles, right? You can imagine that goes on, right? So analytes can just go straight down the side, or they can take a more circuitous route, maybe going in and out of particles, right? Okay, and the analyte molecule that comes out, right, uh, that comes out first in this case is going to be A because it has chosen the most direct route, right? Also, this is how size exclusion chromatography works, right? B is diffusion, which we just talked about, okay? So I don't think we need to go over that much more, right? Diffusion is a function of the diffusion coefficient and time, right? Right? Uh, and so the only way we can, we can either change the diffusion coefficient, which is and has inherently almost impossible to do, uh, unless we change the force of friction in our mobile phase and our stationary phase somehow, or we can change the amount of time that an analyte spends in the column, and that is going to be related to the flow rate. So you can see where that inverse proportionality comes in. Okay. The one thing we haven't talked about so far, is the mass transfer. Okay. So, I need a pen. We consider a stationary phase molecule. Okay. Our analyte has to interact with it. Okay. And if that interaction is very sluggish, okay, if it takes a really long time for that analyte molecule to come off, all right, then more of the analyte that didn't interact is going to get passed, right? And so what ends up happening is you get this kind of lagging thing going on in your column, okay, due to sluggish transfer kinetics, right? And that can be either due to sluggish transfer kinetics off of the solid phase or into the mobile phase. So typically the Van Deemter equation is simplified as A plus B over U plus CU. Okay? All right. So that covers band broadening. And I think that will cover this recording as well. So we will talk more about column selectivity factors and other things next video. Column retention, that kind of stuff. All right. See you then.